Well, hello everyone. We're continuing our work in our chapter on aldehydes and ketones, again picking up with the general types of reactions that they're able to undergo. We spent time in the last lesson discussing redox, the oxidation where we increase the number of C to oxygen bonds, or we can decrease the C to hydrogen bonds. And the opposite of oxidation obviously is reduction. Here we pick up with a new type of reaction known as an addition reaction. In an addition reaction, we take a reactant such as X bonded to Y, and those are just, of course, general letters that can designate any additional reactant, such as HBr or a Cl, whatever it might be. But it's usually just two atoms with a single bond between them, and we're going to add them across the double bond in this carbonyl substrate. When we add across the double bond, we break one bond. Typically the C to oxygen, this double bond here, is broken, leaving a site to add a substrate onto the carbon, as well as to complete the octet of the oxygen. So just to emphasize as we're kind of looking at it, one of these bonds, the double bond here, is broken, leaving a new site of attachment on the carbon to complete its tetravalent requirement, 4 bonds. And of course, then the other component would add on to the oxygen. So let's take a more specific look at this. And we'll focus specifically on forming what we refer to as acetals and hemiacetals. These vocabulary words, the acetals and the hemiacetals, are the products when aldehydes undergo reactions with alcohols. Now let's emphasize, the aldehyde we understand is always at the terminal end of a carbon chain. So here is an aldehyde where we have a carbonyl oxygen bonded to the hydrogen, terminal end of a carbon chain. And we're adding across that an alcohol, an ROH group, an alcohol. And what happens again, if you remember, we break one of these bonds, break one bond in the double bond, and that creates a site of attachment to add one of those things to the oxygen and the other to the carbons. We fill the octet of both of those atoms. And this right here, remember, this is what we refer to as an alcohol. So we have an aldehyde with a carbonyl, could be a ketone, but here we're forming first with an aldehyde in our first example. And then we add an alcohol, ROH. And of course, this is the presence of an acid, which is just really a catalyst. Not really a reactant, not a product, so it sits on top of the arrow. Now look to see what's happened. This alcohol, ROH, this hydrogen adds on to the oxygen. So just take a look where we landed. Here's the hydrogen from the alcohol filling the octet of the carbonyl oxygen. And the remainder of your group, this RO, is filling the octet on the carbon. Here's an important vocabulary word to notice. This is a hemiacetal. That the original carbonyl carbon, this carbon that used to be bonded double bond O, has now bonded to create an OR-OH configuration. This configuration gives us a functional group, very important to see this, as a hemiacetal. Now, in a second equivalence, if the reaction is allowed to go with an additional mole of the alcohol, we notice that a second step has taken place in which the hydrogen that was originally from the oxygen in the carbonyl group is now replaced as well with the remainder part of the alcohol, the ROH. And of course, there would be a byproduct of water. Notice the water comes from, here's the OH and an H. This is the water molecule. And now notice carefully this vocabulary word. We've formed a complete acetal, and an acetal has the carbon originally from the carbonyl, now bonded twice to OR groups. So here we have an acetal, and here we had a hemiacetal, still having one component of the oxygen left. And this is going to take a little practice, so let's keep looking at it. When we add just one molecule of an alcohol, it leads to a situation where we have a hemiacetal. Here's the carbon that used to be the carbonyl carbon of a double bond. So remember, here is how it started, either a ketone or an aldehyde, but we called this a carbonyl carbon. And in the presence of an alcohol, so we're looking at plus alcohol, the first product to form is called a hemiacetal. Notice where it says one group on the original carbon is an alcohol, OH, and the second attachment is the OR, making it a hemiacetal. If we allow the reaction to proceed with a second equivalent, a second mole, step 2, a second equivalence of that same alcohol, we take off the OH and replace it with the OR, forming acetal all the way around. 2 groups of OR surrounding that original carbonyl carbon. So this is the original carbon that was an acetone or a ketone, and it's now been converted all the way to an acetal group. So just think of this as step 1, step 2, going from a carbonyl all the way to an acetal group. When we think of propanal, here this Al ending, propanal, must be an aldehyde. Al is aldehyde. And we use ethanol added to sulfuric acid. Let's walk through this stage by stage. First of all, I noticed that propanal is a compound with 3 carbons. And at the end of the chain is the oxygen. And that oxygen there creates this aldehyde group. So here is the original compound called propanal. This carbonyl compound contains a C double bond O. All right. And so now it says, let's treat this. So sitting on the arrow is ethanol. And we know ethane is a 2 carbon, CC, and then it would be OH for the alcohol. And of course, as the catalyst will be sulfuric acid. Ethanol is a 2 carbon alcohol. Propanal is a 3 carbon aldehyde. And those are the 2 reactants. Remember the addition. It says in step 1, we break the single bond in the alcohol, and we break one of the 2 bonds in the carbonyl carbon. And those create sites of attachment. And so again, just drawing the 3 carbon that was originally a carbonyl breaks the double bond and creates an attachment for the hydrogen, and it creates a second attachment for the remainder of the alcohol. So just visually, here's the OCC onto one side of the carbonyl carbon, and here is the H. It's not showing up. Here is the H from the alcohol. And the vocabulary word here is just to recognize that this is a hemiacetal. That's the first step in this conversion, is creating a hemiacetal. Now it says, let's take a second equivalence of this alcohol and let it react again. In the presence of sulfuric acid, what will happen next step? Well, again, here's the original 3 carbon chain of the aldehyde, propanal. Right now, it has the oxygen left, and it has the OCC from over here on the hemiacetal. When we think about the reaction, the OCC is going to replace the H. This is where the water byproduct comes from. Alrighty, so here we'll end up with, whoops, let me go back to a pen. The O, and then we just have, let me write this better. I'm going to just erase that oxygen there and make sure that we have that cleaned up clearly. So that when I highlight, I wanted to highlight this CC and the hydrogen will displace. And the H and OH form the water molecule. And so on this compound up above, it will have the mirror image. In other words, these two functional groups are indeed identical from the alcohol that we placed, the original ethanol. And of course, what's not shown, but it is here, is the remainder there of a water molecule. And this is converted all the way then to an acetal group. In your first step, treating an alcohol to a carbonyl compound creates a hemiacetal. And in the second treatment, it goes all the way to the acetal, where the alcohol, whatever the alcohol might have been, here it was methanol. Our example used ethanol with 2 carbons, and we just create that mirror image on the original carbonyl carbon. When we think of using propanal, which is this carbon chain we just drew a moment ago, this is propanal. In the presence of ethanol, the OL ending meaning alcohol, the AL ending meaning aldehyde. When an aldehyde and an alcohol react in its first stage, we produced a hemiacetal. In the second step, we take off this hydrogen and replace it again with the remaining carbon chain of the alcohol, and we produce the acetal. This is the same diagram we drew on the previous slide together. Let's look at one where it involves a ketone. Cyclohexane. Here this ending ONE, that tells me that the compound is a ketone. Cyclohexane. So there's a 6-carbon ring, and I have an oxygen, making it a ketone, so we have a carbonyl carbon. And this time we're going to react it with methanol, which is 1 carbon in an alcohol group in the presence of sulfuric acid. The carbonyl carbon breaks 1 bond and creates a site of attachment for the next compound. So again, redrawing our cyclic structure, the carbon to oxygen bond is no longer double, it is a single bond, and it creates another site of attachment to fill the tetravalence requirement of the carbon. In the first, the H from the alcohol adds to the carbonyl oxygen, and the OCH3, the remaining part of that alcohol group. So just look at where this lands. Here's the H from the alcohol on the carbonyl oxygen. Here's the CH3O filling the 4th bond requirement on the carbonyl carbon. And remind yourself, this is what is called a hemiacetal. If we further treat in a second equivalence or a second mole of methanol, CH3OH is then treated again in the presence of sulfuric acid. And here we go all the way to forming an acetal, which takes that oxygen and creates the mirror image OCH3 on both attachments. We turn the hemiacetal into an acetal with a second treatment. Very simplistic. Great job. Here's the same slide, just giving you a chance to see this visually. Here is the carbonyl carbon. If we highlight that, it might show better. Here's the carbonyl carbon on cyclohexane. ONE is the ketone. We're treating that with methanol, CH3OH. The hydrogen bond breaks away from the alcohol and it places it on the oxygens. And then here, the remaining part of the alcohol is landed on the fourth bond of the original carbonyl carbon. A hemiacetal was formed. In a second treatment, we have mirror images of the original acid and not shown, but we have an H2O, the H2O coming from the remainder part of what was left over from the addition from hemiacetal to acetal. The H2O in addition to the OCH3 that bonded. So a step 1, step 2 in the formation of an aldehyde or ketone turning into hemiacetal and landing at an acetal group. Stop the video for a moment and in your own notepad, try these first. Stop the video, give them a try, and when ready, come back and see how you did. Pause, try it, come back. Welcome back. You must be ready to try your answers. Notice that the question gave us 2 equivalents in the process of an alcohol, drawing the hemiacetal and the acetal. So my first job is to recognize the carbonyl carbon as the site of this reaction. In my first step, I count out 1, 2, 3, 4, 5. So I'm just going to get my carbon chain ready. And I see at carbon number 3, I originally had the carbonyl, C double bond O, but I recognize that I will break the double bond and I will complete the octet using the alcohol on the carbon minus its hydrogen. Since that hydrogen got placed up, the hydrogen from the alcohol adds to the oxygens part of the carbonyl group, and the CH3O fills the fourth bond on the carbon. This is what we refer to as the hemiacetal. In the second equivalence, we still have a 5 bond, and instead now of having an alcohol, we have 2 groups that are identical, forming the methoxide OCH3, and that's the acetal equivalence. Step 1, step 2, forming the OCH3 on both of the sites of attachment on the original carbonyl carbon. Here's your letter B, just for feedback opportunity. This happens to look like an aldehyde, benzaldehyde. So the carbonyl carbon, C double bond O, in the first reaction produces a hemiacetal. And remember to just break the H apart from the alcohol. So in your first product, we'll draw that benzene ring. Here is the carbonyl carbon. Instead of a double bond, we now have a single bond to the oxygen. We still have the hydrogen, and the fourth bond on the carbon ends up to be the OCH2, CH3, and the hydrogen filling the octet of the oxygen. A hemiacetal was formed. In the second equivalence, we drew the benzene ring, and now the carbonyl has identical substituents in both directions, and of course the hydrogen is still on there as well. We have formed the acetal. So I take a look at the alcohol, and I'm going to separate the hydrogen away from the backbone of the carbon chain, and I add those across the double bond on the carbonyl. How'd you do? I put a slide in here to just remind ourselves there is a difference between acetals and the term ether, which we practiced in a previous chapter. We recognize an ether as being an ROR. that these carbons are attached to other carbons or perhaps hydrogens. But what's different with an acetal or a hemiacetal is there's more oxygen attached to a single carbon. There's 2 OR groups on one carbon to make the acetal, whereas there's 2 C's on a single oxygen atom. I look left, I look right, and they're both carbons. Notice I have 2 oxygens on a single carbon. Here I have an oxygen attached to 2 carbons. We must remember the difference between an acetal group and an ether group. So pause there and just ask yourself, how would I label these as ethers, hemiacetals, or acetals? Take the time to write your answer down. Here I have an oxygen attached to 2 carbons. When an oxygen is attached to 2 carbons, that is called an ether. This would be diethyl ether. Kind of the ROR format. And then notice what happened here. Here's a carbon, and it's attached to 2 oxygens. A carbon attached to 2 oxygens we defined as an acetal group. Did you have those right? Try some more. Stop the video. Don't cheat yourself of the practice. Stop the video and label these as ethers, hemiacetals, or acetals, and come back when you're ready to check your work. Don't cheat. Do them first. Okay, welcome back. Find the oxygen. Find the oxygen here. And I noticed that oxygen is attached to 2 other carbons. This is an ROR configuration. Oxygen attached to 2 other carbons is called an ether. Here is a carbon attached to 2 oxygens. When a carbon is attached to 2 oxygens, and you see that carbon, I wanted this guy. I wanted the carbon, and I see it's an OR, we call that the acetal group. Here is the carbon, but this time it's attached to an OH and an OR. When a carbon is attached to an OH and an OR, that's the definition of a hemiacetal. And finally, in our last example, here's the carbon, and it's attached to 2 other oxygens. When we see a carbon attached to 2 other oxygens, it's called an acetal group. Are you doing well? Cyclic hemiacetals are most stable when they have 5 or 6 membered rings. Therefore, there's no ring strain, and we just are asking you to recognize the general formula if you find it in a cyclic structure as well as in a straight chain structure. So when I see a carbon and I see it attached to an OH and an OR, that was our hemiacetal. But remember, it may also be in a cyclic structure. Here's a carbon attached to an OH and an OR. So therefore, I can see that it is a cyclic hemiacetal. Here's a 5-membered ring. Here's a carbon attached to an oxygen attached to an OR group. So it is also a hemiacetal. Recognizing that it can be in a straight chain or in a cyclic structure. Sometimes intramolecular forces cause a reaction of a compound within its own structure to create a cyclic ring that happens to be more stable than the long chain carbon. So we have an OH group from an aldehyde reacting with an alcohol group at the opposite end. So notice what's happening. Here's a carbonyl making it an aldehyde, Al for aldehyde. But down at the other end is an alcohol group, 5-hydroxypentanal. So here, the OH at one side and the opposite end is the aldehyde. Keep in mind, these are all just sigma bonds. They're single bonds and they freely rotate. And if you just simply reconfigure the original 1, 2, 3, 4. Oh, here, duh, I've missed this guy. Let me renumber. 1, 2, 3, 4, 5. Thank you. So I renumbered that, and just to kind of highlight where they ended up, I'm just twisting them around, and I can see that here's the original carbonyl, C double bond O. Here's the original alcohol, OH, and they can convert into a hemiacetal by eliminating the 2 hydrogens. And so they remove this H, they remove this H, and then there becomes a site of attachment, and it becomes a 6-membered ring where the 6th member comes the oxygen. And that's what we refer to as a hemiacetal, an carbon attached to an OH, attached to an OR, a hemiacetal group. And so this was just occurring by rearrangement. And we eliminated minus, if you will, an H2. And that happens just to create a more stable structure. We bring this up to kind of just simply tie in carbohydrate chemistry coming up in a few short chapters away. One of the most common or simple carbohydrates is called glucose, and it's predominantly existing as a cyclic structure. And we can see here that it has a carbon attached to an OH, attached to an OR group. There's a lot of other things happening in that compound as well, but it refers to itself as a hemiacetal, and this is the cyclic structure. So glucose is an example I'm sure we're very familiar with. Its formula, C6H12O6. It's our common formula for glucose. And when it arranges itself in a cyclic structure, it does so using a hemiacetal functional group. In our last bit of talk, we talk about the opposite direction. Hydrolysis is a reversal of the addition reaction. So the acetals can be converted directly back to aldehydes through the process of adding water across the bond. Let's take a look at a general formula. An acetal group is one in which we have a carbon attached to 2 ORs. By adding water, we undergo hydrolysis, and adding water says what I'm going to do is to remove, I'm going to remove the following compound. Here I'm going to remove the original R, OR, and we end up back with the aldehyde or the ketone that we started with. And here are the 2 equivalents of the alcohol. So it did this all in one step in this particular diagram. It says, if I read it this way, I know that an alcohol added to an aldehyde creates an acetal in a 2-step process. And they're just reminding us that we can reverse the reaction through hydrolysis, take the acetal and bring it all the way back to the original aldehyde or ketone. That this is a reversible reaction. So just the moral of the story is both the forward and the reverse reaction take place. And thinking about what bonds break and what bonds form, if I start with the acetal group means that I have a carbon attached to an OR group twice. The bonds that break were originally from the carbonyl carbon. Adding water across those dehydrates that. Adding water undergoing hydrolysis says, let's take that alcohols back. The original alcohols came from this part of the functional group, and then 2 equivalents would give us the carbonyl group back. So I can tell that this would end up to be a ketone with the longest carbon chain ending up to be the pentanone, and the carbonyl carbon is brought back to C double bond O. Notice that I'm just numbering the longest carbon chain. I'm finding that carbon attached to the 2 OR groups. When I find this carbon, I know that it will simply convert back to a ketone. Shall we try some? Undergoing hydrolysis, just kind of tell yourself that the aldehyde or ketone converts back. So that's our goal. We want to make the aldehyde or ketone. So that's all the note I'm trying to write there. It comes back to us. So originally, I'm starting here. Here's my carbon that's attached to two OR groups. So I'm recognizing this beginning compound as something we've learned to call an acetal. When I number the longest carbon chain without the acetal groups in it, we do not want to number the OCH3. They're going to be removed to make the alcohols. I notice that this is a 5 carbon chain, and on carbon number 2 is the carbon attached to the two OR groups, so it will be restored to the carbonyl carbon, and we would have 2 equivalents of CH3OH alcohol, that the alcohol is coming from the CH3OH. So these are the alcohols that come out here, and on carbon number 2, this is our carbon number 2. This is where we see the return of the carbonyl. So we created 2 pentanone, a ketone. Let's try letter B. Letter B, I'll start by recognizing the carbon that's attached to 2 OR groups. That is the carbon then that will be returned to the ketone. So I'll simply draw that cyclic structure. It's a 6-membered ring. And here the carbon is returned to a ketone, and the alcohol would be 2 equivalents of CH3CH2OH. And in our last one, here's the carbon attached to the 2 OR groups. It happens to be at the terminal end of a chain, so this will end up making a aldehyde. We have a cyclic structure, a 6-membered ring. Here's the carbon that was originally part of the acetal group, and it simply returns itself to the carbonyl function, creating the aldehyde. And the alcohol that would come out would be 2 equivalents of CH3OH. Here we created an aldehyde. And here, since they were deeper in the chain, these were both ketones. And that, my friends, is the end of our Chapter 16 journey. Please record your notes and bring them into the Dropbox. See you in class.